Okay, we'll pick up with this here. So I wanted to kind of finish up section 7.5 here. Now we got 3 more examples left to do. So the next problem is where we're integrating 1 divided by x times the square root of x squared plus 3. Okay, that's going to involve a trig substitution. The giveaway to that is the x squared plus 3, right? So x is equal to a tangent theta. Well, a squared is 3, so a would be root 3. X is equal to root 3 times tangent theta. Okay, tangent theta equals x over root 3. Tangent theta is opposite over adjacent. So in this triangle, the opposite side is x, the adjacent side is root 3. The hypotenuse of the triangle is the square root of x squared plus 3. dx is going to be root 3 times secant squared theta d theta. Okay, and then the square root of x squared plus 3, that's the square root of x is root 3 tangent theta, so it'll be the square root of 3 tangent squared theta plus 3. If I factor out a 3 from that, tangent squared theta plus 1, that's the same as secant theta, secant squared theta, sorry. And the square root of secant squared theta is secant theta. So I got root 3 times secant theta. Okay, and then when I fill in the integral with the substitution there, I had dx is root 3 secant squared theta d theta. Now that's good. Divided by x is root 3 tangent theta times the square root of x squared plus 3, that's root 3 secant theta. Root 3's, those will cancel. Okay, and that 1 over root 3, that'll come out of the new integral there. So the next thing, if I divide secant squared theta by secant theta, that's secant theta. So I got secant theta divided by tangent theta. Secant theta is by definition 1 over cosine theta. Tangent theta is by definition sine theta over cosine theta. So when I flip the denominator there, the cosine thetas will cancel. That's going to be with 1 divided by sine theta. 1 divided by sine theta is by definition cosecant theta. Okay, so we got 1 over root 3 times the antiderivative of cosecant theta. We've already seen this integral before in section 7.3 was where we saw that. And there's a sneaky little trick here. You want to multiply the top and the bottom by cosecant theta minus cotangent theta. So that's what I did here. And let's see, when I distribute, I got cosecant squared theta minus cosecant theta cotangent theta. And then I'm setting myself up for a u substitution there. So if I let u be the denominator, cosecant theta minus cotangent theta, du, the derivative of cosecant theta is negative cosecant theta cotangent theta. And then minus, the derivative of cotangent theta is negative cosecant squared theta d theta. So minus and negative means plus. And that's exactly what I'd have in the numerator there. Okay, so I'm going to be integrating 1 over u du, which is the ln of the absolute value of u. U is cosecant theta minus cotangent theta. So the when I replace theta with when I replace cosecant theta with things involving x and cotangent theta with things involving x, cosecant theta is hypotenuse over opposite. So when I refer back to this triangle here, the hypotenuse is the square root of x squared plus 3, and the opposite side is x. Okay, minus cotangent theta is adjacent over opposite. Okay, so the adjacent side is root 3, the opposite side is x. And I guess you can combine these to a single fraction inside the absolute value bars if you want to, but this would be my answer there. Okay. So let's see. Let's try. We got two more examples here. What if we want to integrate secant theta tangent theta d theta divided by secant squared theta minus secant theta? Okay, well I know that the derivative of secant theta is secant theta tangent theta d theta. So the first thing I'm going to do here is use the u substitution. If I let u be secant theta, then I'm going to integrate 1 divided by u squared minus u du. Okay, using common of those two terms in the denominator so I can factor that out. And so here's where I'm at so far. We'll need partial fractions for this problem. So 1 divided by u times u minus 1. Both those are linear factors, so that's going to be equal to a over u plus b over u minus 1. And then if I multiply both sides of this equation here by u times u minus 1, I'll have 1 equals a times, the u's will cancel there, so a times u minus 1, that's au minus a, plus b times the u minus 1 terms will cancel, so plus b times u. Okay, and then if I group the terms together, so a plus b times u minus a is what I've got at this point. Now I'm going to match things on the right with things on the left. I don't have any u terms on the left, so a plus b equals 0, and negative a equals 1. Okay, well, if negative a equals 1, that means that a equals negative 1. And a plus b equals 0 means that b would be 1. So I know a and b now. And now when we go back to the integral, okay, and replace a with negative 1 and b with 1, that allows us to get the antiderivative. So I got negative the ln of the absolute value of u plus the ln of the absolute value of u minus 1 plus a constant. U is secant theta, so replace that. My answer then would be negative the ln of the absolute value of secant theta plus the ln of the absolute value of secant theta minus 1 plus c. Okay. One more example here. This was in your book. I'm not sure if it still is, but say change additions and whatnot. But so anyway, this problem here is what we'd like to integrate. Now, the thing to start with here is, so I know that the derivative of tangent theta is secant squared theta. Okay, so I'm going to multiply the top and bottom by 1 over cosine theta. And say theta, 1 over cosine x. So sine x over cosine x, that's the same as tangent x. And I got tangent x times cosine x in the denominator there. And then ln of tangent x divided by cosine x is in the numerator. Okay. 1 over cosine x divided by cosine x, when I flip the denominator, that's 1 over cosine squared x, which is by definition secant squared x. Okay, so I'm setting myself up for a u substitution here in this problem. I know that the derivative of tangent x is secant squared x. So if I let u be the ln of tangent x. Now you could let u be just tangent x. That's fine. You need two substitutions then afterwards. But if we let u be the ln of tangent x, then the derivative of the ln of x is 1 divided by x times the derivative of x. Okay, so I got 1 divided by tangent x times the derivative of tangent x is secant squared x dx. Well, that's what I have in the numerator there. Okay, so I'll be able to knock out that part. U is the ln of tangent x, so I'm going to be integrating u du. Okay, now this is a definite integral, so I've got to change the bounds. Right now they're in terms of x. So if x is pi over 4, tangent to pi over 4 is, let's see, 1, and the ln of 1 is 0. When I plug in pi over 3, I got tangent of pi over 3, that is root 3 divided by 1. So the ln of root 3, that'd be the upper bound. Okay, and then now I can get the antiderivative here. It'd be 1/2 u squared, and I'm going from 0 to the ln of root 3. Okay, when I plug in the bounds, plugging in 0 is not going to make any difference there, but I got 1/2 times the ln of root 3 squared. Okay, now I'd be okay with you leaving your answer in this form. Your book will take this a little bit further, though. The ln of root 3, the same as the ln of 3 to the 1/2, and powers can come out of logarithms. So you're going to have 1/2 times the ln of 3 squared. 1/2 squared is 1/8, right? So I got 1/8 times the ln of 3, and that would be another acceptable answer that you could give there. Okay. So this was like problem, it's one of the problems near the very end of the section. So, which is, it kind of makes sense that it's not problem 1, okay? But there's some algebraic manipulation going on. There's a u substitution going on, and yeah. So, okay, that's it for section 11.5 there. So this is the homework there that you're going to want to look at. And we'll go ahead and stop the video right there.